Hello everyone and welcome to Robotics and Aerospace tutorials. In this tutorial, we provide a concise introduction to rotation matrices in robotics and aerospace engineering. We explain how to derive the rotation matrices for the two-dimensional case. However, everything explained in this tutorial can easily be generalized to the three-dimensional case. Let's start with the problem formulation. Consider this graph over here. This line represents a cross-section of the body that can rotate around the point B. Over here, B in these parentheses is actually a notation for the body frame. This body frame is fixed to our body and it can rotate with the body. Then we have this point P of our body. The point P also rotates with the body. This vector over here, that is the vector RP with respect to B, is the distance of the point P from the origin of the frame B. That is from this point over here. We assume that this vector creates an angle of beta with respect to the horizontal axis of the frame B. Next, we rotate the body for the angle of theta, and as the result we obtain this graph over here. Over here, to make the graph to be less busy, we will not show our body. So what's happening over here? Since the body rotated for the angle of beta and the body frame is fixed to the body, this body frame B will also rotate for the angle of theta. The same thing will happen with the point P. The point P will also rotate for the angle of theta, as well as this distance vector RP with respect to B. Next, we have this inertial frame, denoted by S, with the axes XS and YS. And this frame is fixed. That is, it doesn't rotate. And initially, the body frame has the same orientation as this inertial frame S. To formulate our problem, we need to introduce the projections of the vector RP. That is, the projections of the distance vector shown over here. The vector RP with the representation in the frame B has these projections. The projection of this vector over here onto the XB axis of the frame B is constructed like this. We create a line that creates an angle of 90 degrees with this axis XB. Then the projection is actually this distance over here, from here to here, measured on the XB axis. And this projection is denoted by XB of the point P. Similarly, we construct the vertical projection by drawing the line that creates an angle of 90 degrees with the positive direction and with the line YB. And this projection is measured from here to here, and it's denoted by YBP. To repeat, RPB is expressed like this. It has projections onto the X and Y axes of the body frame B. Then we have another vector, or better to say the same distance vector with different projections. This vector is denoted like this. It is denoted as R of the point P, that is the distance of the point B, expressed in the frame S. And let's find these projections. What we need to do is to find the projections of this vector onto the horizontal and vertical axes of the frame S. And obviously, again, we draw a straight line that creates an angle of 90 degrees with the axis XS, and the distance from here to here is the projection, and we denote it like this XSP. Similarly, we construct the projection onto the y-axis. We go from this point, we draw a straight line with the angle of 90 degrees, and where this line intersects the axis ys, we will obtain our projection. And the projection is from here to here, and it's denoted as YSP. And these are the two projections. Now we are ready to state our problem. Here is the problem. Given the projections of the vector RPB, that is, given XPB and YPB, and given the angle of rotation of theta, we need to compute the projections of the vector RPS, that is, we need to compute XSP and YSP. Let's explain this problem formulation graphically. We are given this projection over here and this projection over here of the vector RPB. And we are given this angle of rotation theta. And we need to compute this projection and this projection of the vector RPB. In this tutorial, we will show that the solution to this problem can be represented as a single matrix vector multiplication. That is, we will show that the projections of the vector RPS, that is, this vector over here, XSP and YSP, is equal to a matrix that's usually denoted by R and that depends on the angle of theta, multiplying the vector, or better to say, multiplying the projections of RP in B. That is, multiplying XBP and X and YBP. This matrix over here is called the rotation matrix. And in this tutorial, we will derive the expression for this matrix. However, to understand this matrix and its purpose, you first need to understand how to solve this problem. Let's derive the solution. For the presentation clarity and to simplify the notation, let us first denote the intensity of this vector, that is, of the vector RPB, simply by R. That is, R is equal to the intensity of the vector RPB. Next, from this figure over here, we have XSP is equal to the intensity of this blue vector, denoted by R, multiplying the cosine of the angle theta plus beta. So let's write it down, cosine of the angle theta plus beta. Then, we can see that YSP, that is this projection, is equal to the intensity of this blue vector multiplying the sine of the angle of theta plus beta. Okay, next, we need to use the formula for cosine and sine of the sum of the two angles. And here are the formulas. We have cosine of theta plus beta is equal to cosine theta multiplying cosine beta minus sine theta multiplying sine beta. Similarly, we have that sine of theta plus beta is equal to sine theta cosine beta plus cosine theta multiplying sine beta. Okay, now let's substitute these two equations in these two equations and let's see the result. We have that XSP, that is this projection over here, is equal to R multiplying this first term over here minus R multiplying the second term over here. Then we have that YSP is R multiplying this term over here plus R multiplying this term over here. Next, let's simplify these expressions. First of all, from this graph over here, we can see that XBP is actually R cosine beta. And we have that YBP is actually R sine this angle. That is sine beta. If we substitute these two expressions in these two equations, we will obtain the following two equations. And let's change the color. We will obtain that XSP is equal to, let's see, we can see here that we have R cosine beta. And instead of that, we can simply write XBP. Consequently, we will have XBP multiplying cosine of theta. Then, let's analyze what's happening over here. We will have R sine beta, and R sine beta is YBP. So we can write minus YBP multiplying sine theta. And here's our first equation. How about the second equation? Let's see, YSP is equal to, let's see, R multiplying cosine beta is simply XBP. So we will have XBP multiplying sine of theta. Then we will have plus R multiplying sine beta is obviously YBP. So we will have YBP multiplying cosine of theta. Okay. Next, let's write these two equations in the matrix form. They can be written like this. Over here on the left hand side, we will have a vector XSP. Better to say, we will have a vector with the projections XSP and YSP. Then over here, we will have a matrix, and we will fill in the entries of this matrix later on. However, for the time being, let's fill in the entries of this vector on the right hand side. On the right hand side, we will have XBP, and we will have YBP. Okay, now what we will have inside? Inside of this matrix we will have, this term will go over here. So we will have cosine of theta. Then this term over here with the minus sign will go over here. We will have minus sine of theta. Then over here we will obviously have sine theta, and over here we will have cosine of theta. And that's it. This is exactly what we are looking for. We are able to transfer the coordinates of the vector RP expressed in B to the coordinates of the vector RP expressed in S. And this matrix over here is our rotation matrix, r of theta. That is, this is the rotation matrix. And let's write it down.